Hi, I'm AJ Bruce. I made Aliyah in 2011 from America, as you could probably hear. I've been living in Jerusalem since 2014. I did a first degree in computer engineering at Hebrew University and a second degree also at Hebrew University in computer science, and now I'm at Lightrix, so I haven't gone far. And I've been at Lightrix for a year and a half. Today I'm going to be speaking about bringing state-of-the-art image-to-image models to the world. So a little bit about the research department in Lightrix, and specifically the research department at Lightrix in general. Lightrix is a company founded in 2013 by 4 PhD candidates who decided to take all the really amazing skills that they were learning and developing and bring it to the industry and build the most technologically advanced photo and video editing apps that are on the market for the consumers. So since then, since 2013, we have over 600 people working across the world, from Chicago to China, but specifically in Jerusalem on Givat Ram, towards this mission. And I'm part of the research department. So the research department is about 35 researchers who are really actually doing the technological advancements in the state of the art. We're taking ideas and models and things that are developed in academia and bringing it to the industry and specifically to users like any of you if you want to download our apps. So I'm on the face team. Here you can sort of see an example of what the Facetune looks like. And I'm on the research team that works on face editing technology. And our most well-known application, Facetune, is based on face editing technology. So we take pictures of users and we give them all sorts of cool effects that they can use. We can do it on our CEO, we could do it on random employees, we could do it on you, whatever. And specifically today, you came to learn how to level up your game. So I'm here to talk about how to bring academic research to the industry, what it looks like to follow what's going on in academia, how you can take that and bring it into your projects, and also what to look out for, because it doesn't always work. We're going to talk about all of this through the lens of my project that I've been working on for quite a while, as you'll see. And we're going to also talk about diffusion models, which are really exciting lately. And if you haven't heard about it, go home and look it up. But you'll see a few examples about diffusion models and why they're really crazy and disrupting the world of digital art and creativity. And it's just an amazing explosion of research, and it's just really exciting. So we're going to talk about that too, which is a bonus. Okay, so specifically my project is hair restyling. We can see here the dream. We have a face image, and we have a tool for editing the hair, the style, the texture, the color. But it looks natural, it looks original. The face and the background and the torso were untouched. And it's something that you would probably want to send to your grandma if, it's not embarrassing. So the naive approach would be just to take a picture, take another picture, paste that hair onto this picture, and it doesn't work, as we can see here. We lose the original global hair texture. It doesn't look natural. The geometry's off, the lighting's off. It looks like a really bad wig. So we're not going to go for that. The first approach that I went with for this project was autoencoders, an image-to-image neural network. So let's look at what an autoencoder is. An autoencoder is an image-to-image network, meaning you start with an image and you get an image. And it allows us to preserve the identity of the input image. It does this by training with a loss that says, okay, the output needs to look like the input. Super easy. You can train it with any images you want. And then because it goes through this encoder and we get a latent code, we can do all sorts of different manipulations to the latent code. And then the decoder will translate those images into a natural image, because that's what it was trained to do, is to develop natural images. So basically, this is cool, but it's not exactly what we want. It doesn't, give us the structural changes that we would want. So we also have a swapping autoencoder. So swapping autoencoder basically is an academic work by Tae-Sung Park from 2020. It wasn't for hairstyle transfer. They did it because it's an academic work. They wanted to see what would happen, and they wanted to be able to take a latent code from an autoencoder and separate it into the style and the structure. and then still have the autoencoder image-to-image capabilities, but also be able to edit either the style or the structure. So if you can think about the structure, imagine if you have a building here. The style code would basically tell you if it's going to be brick or cement or concrete, or I don't know what other type of houses they have, Jerusalem stone. And the structure code would be everything. Okay, so style code for buildings is like that, but style code for people would be the skin color, the hair color, maybe the background, maybe the lighting, makeup strength, all those things that are very global. And then everything else would be the structure code right here. So the structure of the face, the structure of the hair, sort of the global geometry. Hold on, I don't want to forget anything because this is important. Okay, we didn't forget anything. So basically that's the swapping autoencoder. So how can we use this for the task of hairstyle transfer? This is the flow that I developed based on the swapping autoencoder. So basically what we do is we have the structure code, and the real magic happens in the structure code. We have a mask of the hair that we want to have, and then all the regions of the hair from the reference image, we want to take her hair and give it to her. That's reference, hair, source, image. The white is the hair from the reference image. So in all of the regions of the white, we're going to take the structure code from the reference image. Just copy paste. And all the rest, the black, is coming from the source image. So what that leaves us with, the face, the hair, not the hair, the background, and the torso. And we really just kind of copy paste it together, and that's our structure code. And then the style code, we're taking directly from the source image. So we're going to get the original lighting, we're going to get the original hair color, it's going to get the original whatever else belongs to hair. And then we send that through the decoder, and our final image has the structure of the reference image's hair and the style of the source image. Amazing, we're done. That's it, we finished. Very exciting. No, that's not it. Sorry. There's shortcomings, of course, obviously, because what would I talk about? We'll see them here. For example, there's cases where the source image is hair and the reference image doesn't. If we're going from short hair to long hair, so what do we do with the torso? We have to learn how to in-paint it. That's not such an easy task because there's so many different types of textures of torsos. So that's an open question. Or for example, if I have hair over my face, okay. So if I want to give it like a slicked back hair look, what kind of face do I give it? Can I copy paste the reference image's face? Or do I need to learn how to in-paint it with a separate network? That's another example. You can see a few examples here of the in-painting issues. Some of them look okay, but most of them don't really look okay. So here's a shortcoming. Here's another shortcoming, which you might not think about, but this goes back to bringing ideas from academia to industry. So in academia, a lot of these image-to-image models that are trained on faces are trained on a data set called FFHQ, which are really tightly cropped 1024 resolution images of faces, which is great. It looks good, it works. They have it at all the conferences. You can't get away from it. But at Latrix and many other industry applications, we want to have pictures with larger crops, with more resolution, with torsos or backgrounds or whatnot. And so if we can, we saw that it looks really good on these crops, but it doesn't necessarily look really good on these crops. And if we only have these crops, we're missing all the really exciting long hairstyles. So maybe we could just train the network again. But retraining networks, you don't always get the same results. You have trade-offs. You have a larger resolution but a smaller face. It's still an open problem. So that was another shortcoming. Another one, pose and geometry, goes back to the fact that this swapping autoencoder wasn't developed for the task of hair restyling. Hair, the geometry of the hair, while when you take when you composite the structure code from the source and the reference images, it might look natural in the same hair color and the same lighting, but there's a lot of other things that go into it, such as the pose and the geometry. So if the source image is looking up and the reference image is looking down, as in the first row, we can see it sort of looks plopped on there like a wig. It's not really the look she's going for. Or if there's a hand in front of the face and the other woman doesn't have a hand in front of their face, and then we kind of have hair growing between our fingers. Not ideal. Or sort of if the head is tilted and then the gravity goes down, but the other one doesn't. So she looks like George Washington on the $1 bill. It's not great. So anyways, these are all issues that you can find heuristics for, you could build more models for, but then you're kind of getting past the point of why we even wanted this model in the first place. Okay, so lots of shortcomings, no solution yet. Back in July, when I was approached to give this talk, I was kind of at the point where I had a lot of shortcomings. I was like, oh man, this is kind of a bummer. You know, like, it looks cool sometimes, it doesn't always look cool. And not only was it a bummer to have a talk at a meetup that didn't always look great, it was also a bummer because, like, my job. Like, I wanted something that looked good so it could go into the product so everyone could see what I've been working on and use this really exciting feature because it's a really exciting feature. Okay, so we're in July, and then all of a sudden, well, first, let's go back. The research department at Lightrix really places a really strong emphasis on staying on top of the academic trends. We have weekly seminars and reading groups and Slack channels, and we're always discussing new trends in academics and, you know, how this can help us, how this maybe doesn't help us, but maybe we'll put it on the back burner for future. So back in July, we're starting to talk at our reading groups about this new thing called diffusion models. And then all of a sudden, everyone started talking about diffusion models. So what are diffusion models? These are diffusion models. These are images that were generated by Dali Stein in 2022. And basically, these images were just generated just from these words. So someone was like, I want to see Yoda angry at losing money in the stock market. You know, market's bad, Yoda's pissed off. Okay, or I want to see Picasso painted by, Batman painted by Picasso. So really, diffusion models take noise and generate images, really beautiful images and creative images, just from words. And like, that's crazy, because whatever you think about, you can make into a picture. Also a video, but we're talking about pictures. So if we can do this with pictures and Yoda, like, let's try to do this with hair. Okay, before we talk about hair, let's talk about diffusion models and like how do they actually work, and then we could talk about hair, because hold your horses. Okay, so basically when we say we're taking noise and creating images from it, we're basically taking noise and then step by step by step by step by step, we're gonna take away some of the noise. We're gonna learn what the noise is and take it away, and then use that to generate an image. And at the end of the day, we have an image. How do we train something to see the noise and take it away? So let's build a data set where the input is an image, a noise, wait, hold on. Basically, we could take a data set by taking an image and then adding noise, and then taking the image and the noisy image and the amount of noise that was added, and then that will be our input to a network. So we have a big data set where we have an image, and where we have it slightly noisier and slightly less noisier, and we know how much noise was there, and we use that to train a really pretty simple module, really simple neural network that we're going to call the noise predictor. It's going to look at this image, and it knows it's been trained to say, okay, this is the noise, and then because we know what the noise is, we'll take it away. So basically, we're going to be able to, once it's trained, take a noisy image, send it through the noise predictor, and then get another one. And we take that noise away. And then we keep going, keep going, keep going, until we get a less noisy image. What does this actually look like when we use it? We send in random noise to a noise predictor, and then it loops through however many times we tell it to. So in this case, t times, and we go from noise to an image. Okay, this is really cool, but not that cool, because like, where are the words that I get to tell it that Yoda is pissed off at the stock market? Here we go. So instead of having just any old noise that's being predicted into an image, we could also condition it on text. We can take images, and we know, because we have large data sets of images and text captions, we know we can also send in text as an option for the conditioning. And so instead of sending in random noise and just unconditionally creating an image, we could tell it, oh, I want a paradise cosmic beach. And it creates this beautiful paradise cosmic beach that never existed until now, until we generated it. Great. Okay, what if I actually wanted to edit an image that already existed? So instead of starting from random noise, we take an image and we noise it, we add noise to it, we send it through this conditional noise predictor, and we say, I want a pirate ship. So then when it's denoising it, it knows that there needs to be a pirate ship, so it adds a pirate ship in a way that looks very natural because it knows how to generate natural images. And at the end, we have a beautiful cosmic paradise beach from the last slide with a pirate ship from this slide, a beautiful piece of art. Great. Okay, still doesn't give us hair. Where is the hair? Here's the hair. All right. So basically, in painting is a subset of the image-to-image diffusion models. We have a diffusion model. We start with an image. We end up with an image, but we also want to edit only in certain places of the image. So I used a process described by Omri Avrahami, who's a PhD candidate at Hebrew University, in his paper, Blended Diffusion. He actually came to present this paper to us, which is really exciting because that's another way that at Lightrix we stay on top of things, is we have people to come and explain it in their own words. But basically what we do is we take this image, and only in the places where we're labeling, so basically only in the hair region, or if we wanted longer hair, we can make the hair region longer, shorter, larger, whatever we want. Only in that region do we want it to change to light purple hair. Everything else we want to keep the same. And what we can do is we send it through the conditional noise predictor, but we could also composite the output of that with just the image that went through some noise. And we do the same process, and each time we composite it according to the mask that we described earlier, and we get this amazing picture of this woman with the purple hair, which is so fun because this is the kind of result that I wanted for like months. I'm like, ugh, I can't get there. But here we are, we're there. And it's all because of diffusion models. So, very exciting. Oh, sorry, I jumped the punch. Okay, obviously there's shortcomings. I want to start with the shortcomings so we can end with the cool results. Here are some shortcomings. Beautiful. Not going to send this to grandma. Anyways, so with diffusion models, it doesn't learn the context of what a human face should look like. It does, but it doesn't. There's already an eye here, but it doesn't really necessarily understand the geometry of the face or the structure of the face. It was trained on images of faces, but it was trained on a whole bunch of other things. And so there's really sometimes these amazing artifacts which are frightening. There's ways to get around them. There's parameters you can use to you make it less strong. There's ways that you could notice that something like this is happening. So this is not necessarily a game changer or a game stopper, whatever the word is. But anyways, this is something you can work with. This is not terrible. This is also not terrible. We can figure out ways around this, but it's still a shortcoming. Another shortcoming is that it doesn't yet use, or at least I haven't yet used, a specific reference image. In order to create a certain hairstyle, I need to describe it in words, and I haven't yet gotten to the point where I could take a picture and label the hair and say, I want this hair. I want a picture of Bridget Bardot, I want her hair, or I want Rachel from Friends hair, or whoever, I don't know who's famous nowadays. I want that person's hair, a Jenner person. So that's also sort of something that is room to improve. And then the runtime, it's getting better, but it's still a bit slower than the swapping autoencoder, and especially if you want the resolution to be very high, you need it to either do super resolution or it'll take a bit longer because we are iteratively going through the denoising process, as opposed to swapping autoencoder, you just go through once. So those are the shortcomings, but there are beautiful benefits. Basically, all the benefits are that diffusion models are amazing in magic, but our in-painting, it does in-painting. Basically, it already does in-painting. It either gives it hair in those exact positions, so I'm not taking a reference image that has different hair geometry and giving it to the source image. It'll give you hair exactly where I want you to do. Again, with the pose, like it's generating natural images, and it knows how to generate natural images, so it's giving you like the hair in the direction that it needs to be. Same with geometry, and then the crop size, you're not like limited to a crop around the face. You can send it like a picture, and the face could be smaller, could be bigger, could be like a more of a torso face. So that's a huge benefit from this, as opposed to the swapping autoencoder, which was trained on the FFHQ. So super exciting. Here's some other really exciting results. It's just, you could see it like any text prompt that you could think of about hair, you could generate. So hopefully this will soon be in our products and you can actually see it in real life. Anyways, so in general, you didn't really come to hear about the hair. You came to hear about takeaways. So my takeaways are, it's very important to stay up to date with the trends in academia. You don't know what's going to happen, tomorrow that can solve the problem you've been working on for 4 months. It's really important to keep a finger on the pulse and just make that a habit at work, to know what's going on in that bigger world out there, where it's actually literally their job to just sit and research. And then it's also important to realize that there's different goals in academia and industry. Like, it's okay that they're working on small crops around the face, but for us, it's not necessarily okay. And it's okay that their runtime is longer, but maybe it's less good for us. So that's something that it's important to keep an eye on. And I think also the main thing that I would take away from this is that it's okay if the project you've been working on for a long time, maybe the direction you're going in is not the direction you need to be going in, and it's not an ego game. The fact is that it's just most important that it works at the end, and not that, but I wrote so much code. Like, that's not what's important. What's important that it looks great, and then you could talk about it at meetups. So that's my talk. If anyone has any questions, you can ask me now or afterwards, or you can find me on internet. But I think we probably have a few minutes for now. Thank you also. Thank you. Yes. Do I? Maybe I have some thoughts. Yes, Michal asked if I have any thoughts about going from the text-based input to an image-based input. And yeah, I guess I do have some thoughts, but they would be classified. No, I'm kidding. I don't know, I wonder, like, you could probably do a composition like I did with the swapping autoencoder, but I think that you would probably get to the same sort of issues of the geometry and the pose and the in-painting. It might be better because, like, iteratively it'll learn to generate. But as of right now, I have thoughts, but they're probably not successful thoughts. But I'll keep you updated. Anyone else? Yes? Oh, what's your name? Nisan. Okay, so Nisan asked if I came across any issues in implementing or using works specifically here or in general from academia. Because I could say both. Like, specifically here, there's things. So basically at Lightrix, we have a really great team, which Nomi is a part of, that is actually implementing the using the stable diffusion model that Hugging Face released open source, but also like making it so that every other team in Lightrix can use that and develop apps around it. So that's something that was really great, and that's a lot of hard work from the other team in research. And for the other two works, swapping autoencoder and the blended diffusion models, swapping autoencoder, it's on GitHub. It's really easy to use. I think it was like the first project I kind of touched when I got to Lightrix, and then I went away, and then I came back. And so that one was really easy to use, and in general, a lot of things in academia and also just in the world now are being released open source, which is really exciting, and it's like become very collaborative. So specifically that, and also Omri's was not very hard to implement. So it does vary though. It's not always like that. But kind of like if it's super hard to implement, maybe I'm not gonna go in that direction. Cause like, you know, time is money. Anything else? Yeah? Oh, what's your name? Oh yeah, Carmel. You asked a question before. Nice. So Carmel asked if there's ever goes the other way where something we develop in-house, we release open source. Oh, that's a really good question. I'll have to talk to our lawyers and get back to you. I actually don't know the answer. I'm gonna probably go towards like less, just because we're a private company. Um, Maybe my manager knows. Oh, you know what? Yeah. You know, actually, I have a good answer to that, is that we give back to the community other ways. For example, talks like this, or Nomi in 2 weeks is going to be giving a boot camp in Tel Aviv. If you're interested in diffusion models, you should definitely come, and we're going to actually like build them. That'll be super exciting. But also there's blogs, there's conferences that people at Lightrix have presented at. So there's definitely giving back to the community. It's not necessarily like writing papers all the time, because that's not the point of what we do. But we definitely like try to be active members of the research community. I think maybe one more question, or no more questions? No? Okay, thank you. Oh, here we go. I will let you all know, and then I'll send you all like a reminder to download our app so you can use this cool hair to give yourself cool hair to send to your grandmas, your parents, or me, and it'll be very exciting. So thank you all for listening. This is really fun, and I'm really, really excited to be here. So, bye.